Hey everybody, it's Mrs. Bianchi. We're looking at 6A, 6B, and 6C. Ming has 15 quarters, 30 dimes, and 48 nickels. He wants to group his money so that each group has the same number of each coin. What is the greatest number of groups he can make? And if you look at part B, they want to know how many of each coin will there be in each group. And if you look at part C, they want to know how much money will be in each group and how much will it be worth if you get the total. So let's go back to what we need to do. Whenever you see the words greatest number of, then you're probably going to be looking at finding the GCF. And when you also see same number of, coupled with the idea that you have to answer multiple questions about the same grouping, then that's when you want to think about distributive property. All right, so that means if we need to find the GCF, we need to go ahead and either list out our factors or use prime factorization. So let me move these labels out of the way because we're going to come back to that idea. So we have 15, 30, and 48. We need to find the prime factorization for each of those numbers. So I'm just going to draw a line here to separate our workspace. But if we're going to find the prime factorization for 15, something times something equals 15, we would want to try to come up with a number that we suspect as being the GCF and put that suspected number in all of our lineups. So let's say we think it might be 3. If we put a 3 here and a 3 here, and how do we know that 3 goes into this, by the way? We know that 3 goes into it because if we add the digits, it equals 12. And since 3 goes into 12, that's how we know 3 will go into 48. All right, so what are the other factors? Over here, this would be times 5, and that tree would be done because these are prime, both prime numbers. Over here, it would be a 10. And if we kept going on that composite number, we'd get the 2 times 5. And then we would bring down the 3, which it'll be more evident why I have that in red font in just a moment. And over here, you may not know how many times 3 goes into 48, so that might force that algorithm off to the side. So if we actually did the algorithm, it would go in once, and we get the 1 left over, bring down the 8, and 3 would go into 18 6 times, and it would work out evenly. All right, but many of you have that number fact in your head, so it's 3 times 16 that equals 48. Now 16 is not prime, it's composite, so we would keep going, and we'd bring down the 3, and then we might keep going on each composite number. So 2 times 2 would equal 4, and 2 times 2 would equal 4, and then we wouldn't want to forget about the 3. All right, now in class, we talked about how if you're going to find the prime factorization of 3 numbers, the GCF of 3 numbers, then your best strategy is to go ahead and write the numbers over here like so. So this is for 15, and then we'll just copy this maybe in a different color. How about 3 times 2 times 5, and we'll put the numbers in order from least to greatest whenever you can, although I didn't do that here. And then here we have 2 as a factor 4 times. We'll put that all in purple. And then we have the 3. All right, so basically why rewrite it organized like this? It's because it might make it a little bit easier for you to find the matches that are what I call a triple whammy match. It has to match in all 3. But even in the tree, you can see what's a match in all 3. See, we have this 3, we have this 3, and we have this 3. And remember, we're only looking at the prime factorization. So in other words, what I have in the yellow circle. You wouldn't want to look higher up in the tree for numbers that are composite. So we do have matching 3s. Now, if you line it up this way, then one way that you might be able to see that is you would see the matching 3s here, and you would circle them. Now, you would look for other matches that would be in all 3, and there aren't any others that are in all 3 prime factorizations. In other words, the blue one, the red one, and the purple one. That's the only one. So that's going to be the GCF, and we're going to go ahead and put it as that number on the line. Now, once you have that number, this is the GCF, but 3 what? 3 what? Where should you look? If you look at the words in the problem, it says greatest number of groups. Groups. So groups, and that would really be groups of coins. Groups of coins. All right, so now we have to ask ourselves, what, actually, this is even wrong because I don't even have this. Let's get this a little bit bigger because we don't have two, we have three things to be concerned with. We need more space. See if I can move this over just a bit. There. Okay. So what are the three different groups that we're dealing with here? Let's move that three over a little bit. We have three groups, and the groups are going to be, we're going to have a bunch of quarters, we're going to have a bunch of dimes, and we're going to have a bunch of nickels. So 3 times what equals the 15 quarters? And that's going to be 5. 3 times what will give us the 30 dimes? And that would be 10. And 3 times what would be 48? And we already know by doing the algorithm over here that that's going to be 16. All right, so when it says what is the greatest number of groups he can make, we're going with this number, 3 groups. When it says how many of each coin will there be in each group, let's use our organization right here. We will have 5 quarters, 10 dimes, and 16 nickels. So look to see if that's a choice. 5 quarters, 10 dimes, and 16 nickels for 6B. Now here's where it gets a little tricky because it says find how much money each group will be worth. What is the total amount of money? So if we have 5 quarters, then what's that computation? A quarter is worth 25 cents. So you have to find 25 cents times 5. Dimes are worth 10 cents. And we have to multiply that by 10. Nickels are worth 5 cents. So we have to multiply that by 16. Now, because this, I'm going to put the 16 on top. I'm going to put this on the bottom just to make the computation just a little bit easier. All right, because remember, you can change the order of the factors and it does not affect the product. That's community property. All right, so if we kind of press on with what is this total? This times this would be 25. And this times this is 10 plus the 2 more would make that 12. And then we have to remember to go over 1, 2 with the decimal, over 1, 2. All right, so that's $1.25 for the quarters. Quarters, we have $1.25. Actually, let's put that back. I'm just going to rewrite it. $1.25. All right. Now, anytime you're multiplying any number by 10, it's the same as moving the decimal over 1 to the right. So if I move this over 1 to the right, wouldn't that go right here? And that would end up being a 1 or $1. So we have $1 for the dimes. Now, if that didn't make sense to you, then you would just do the algorithm for it. All right, over here, let's do the algorithm. 6 times 5 is 30. 5 times 1 is 5, plus that would make that 8. But we have to go over 1, 2, over 1, 2. So that's 80 cents. 80 cents. Be careful to line up your decimal. And feel free to put a 0 there to clarify that we don't have any dollars. All right, so the only thing left you have to do is add, because that's what it suggests when it wants to know part C. Total amount of money would suggest we're adding all of these numbers. So just be careful to add it carefully, and you'll get one of these choices. All right, good luck finishing it up.